Hello, AP Physics students. So I wanted to clarify some of what we went over today in our lesson since I thought it could be improved on my own end. So reading this problem. A cart begins from rest at time 0 from a long incline, rolls downhill with constant acceleration. At time t, the cart has rolled the distance d from its starting point. How far will the cart roll if it was 5t? So the first thing that I want us to know is, without any formulas yet, what we're comparing is the displacements when we have different times. So let's first find the relationship between delta x and t for situations of acceleration. So distance and time, so that we would find delta x equals v naught t plus 1/2 at squared. They tell us that this thing doesn't matter because we start at rest to begin with. So really, the only relation that we want is that delta x is proportional to t squared. All that other stuff doesn't really matter. We just want to focus in on that. So I'm going to put a quick box around that because we're going to refer to this quite a bit. The next thing that I want to do is make just a little table here. So we're going to have our first run and our second run. And we've got distance and time. So let's say that first run we covered a distance 1 in a time 1. I'm just going to make up those two numbers because later we're going to compare these second run numbers back to those first run numbers. So if the time of the first one was 1, then the time of the distance of that second run was 1. So if the time of that second run was 5, what would be our displacement right here? So we take that 5 and we plug it into t squared to get our guess at what's going on right here. So we've got delta x is proportional to 5 squared. Delta x will be 25 in this situation. So if the time was 5 times greater, then the displacement was 25 times greater. All right, now this is a pretty straightforward situation. Now I want us to practice seeing what the graph of this might look like. So I'm going to do my graph right here. I'm going to focus again on this. So delta x and t, and since t squared, just as if we were writing y is proportional to x squared, we would have y and x. Here we have delta x and t, and the equation is squared. So let's run these numbers. If my first run was 1, 1, and then my second run, instead of having a time of 1, instead I had a time of 5, if my time is 5, I plug in time for 5, it gets squared. My delta x here becomes 25. So I can start to compare the y values. I can say, oh, these two is now 25 times what it used to be when I am 5 times that. All right, so let's do that second problem now. Let's read it real quick. It says two objects, A and B, accelerate from rest at the same constant acceleration. Object A accelerates for 9 times the distance. How much faster? So we want to compare the final velocity as compared to the distance. That's what we want to compare. Now, I don't know if it's a linear relationship like this. So the first thing that I would do is I would hunt down equations that have both VF and D in them. So I'm going to do that right here. We come up to the top here. I see VF and D. Now VF squared, okay, is related to D. So let me write that down. VF squared is related to D. Now that that's accurate, I'm going to put it in my square. All right, so doing it that first way, where we make a table, I'm going to say A and B, and then we have our VF and our D. Get that squared out just a little bit. Okay, so it gave us lots of information about B, correct? Object A accelerates for 9 times longer than object 1. So since our comparison is back to B, I'm going to call B 1 and 1. That way, when we talk about A, it's easy for me to say, oh, 9 times bigger than B, my distance for A is going to be 9, so that this is 9 times bigger, which makes my life a little easier. So the question is going to be, what happens to that velocity? Now, looking at this, it's kind of difficult to plug it in. So what I recommend is rearrange so that the known, when I say known, I'm talking about the piece of the puzzle that we already know, the 9 right here, has the funky stuff here. So we make that rearrangement would look like having the VF is proportional to the square root of D. Now the reason I do that is that when I look over here, I can just take 9 and plug it in for D. So plug in 9, and it gets square root, and it just kind of turns the crank and spits out the square root of 9 will give me that VF is 3. So again, here's the relationship. If I had 9 times the distance, then I will have 3 times the final velocity. Looking at it the graphical way, same situation. I want to use this one where I've already rearranged it. It makes life so much better. So I've got VF, I've got D, I've got my square root curve. So my first point that I plot is going to be this one that I compare back to, 1, 1. And it says that I have 9 times the distance now. So 9, and then I would plug it in, turn the crank, it would do the square root, so now this is 3. And now the question wants to ask us, how does B, I'm sorry, that's A. How does B relate to A? So if the distance, the distance is 3 times bigger, then the final velocity will be 9 times bigger. Alternately, we could say if the distance is 1/3 of what it used to be, then the final velocity, oh, I misspoke. Oh, these are the D's. Okay. If it's 1/9, if the distance is 1/9 what it used to be, then the final velocity will be 1/3 of what it used to be. Hopefully that clarifies something. If it is successful, let me know, and I'll try to do more of these videos. All right. Thank you very much.